Lecture 6.1, Day 1, Antiderivatives and Slope Fields. This is a picture of two telescopes at Kitt Peak National Observatory in Arizona. And to give you a sense of scale, if you look right here, this is an awning above the door, and then there's an elevator to the top. First, a little review. Consider y equals x squared plus 3. Then y prime equals 2x. Or y equals x squared minus 5. Y prime equals 2x. It doesn't matter whether the constant was a 3 or negative 5, since when we take the derivative, the constant disappears. However, when we try to reverse the operation, given y prime equals 2x, find y, we get y equals x squared plus c. We don't know what the constant is, so we put c in the answer to remind us that there might have been a constant. If we have some more information, we can find c. Given y prime equals 2x and y equals 4 when x equals 1, find the equation for y. First, we find the antiderivative and get y equals x squared plus c. Then we plug in our initial values, y equals 4 and x equals 1. Solving for c, we get 3 equals c. So our original equation must have been y equals x squared plus 3. This is called an initial value problem. We need the initial values to find the constant. An equation containing a derivative is called a differential equation. It becomes an initial value problem when you are given the initial condition and are asked to find the original equation. Initial value problems and differential equations can be illustrated with a slope field. Slope fields are mostly used as a learning tool and are mostly done on a computer or graphing calculator, but a recent AP test asks students to draw a simple one by hand. We will start with y prime equals 2x. We pick a value for x and a value for y, in this case 0, 0. So y prime equals 0. Now we draw a short line segment with a slope of 0 across the point 0, 0. If we choose x equals 0 and y equals 1, y prime is still 0. So we draw another line segment with a slope of 0. If x is 1 and y is 2, once again y prime is 0. So we draw another line segment with a slope of 0. And you can see where this is going because there is no y in the derivative equation. It doesn't matter what y is. If x is 0, we're getting a slope of 0. So we could keep filling these in, but they're all going to be horizontal segments. So let's move over. If x is 1 and y is 0, the slope is 2. So now I draw a line segment with a slope of 2. At 1, 1, the slope is still 2. So I draw another line segment. And we see that once again, because there is no y in the derivative equation, the slope is going to be the same as long as x is 1. So we fill those in. This speeds up the example problem anyway. If x equals 2 and y is 0, then the slope is 4. So I draw a steeper line segment with a slope of 4. And I fill those in. Now at x equals -1, the slope is -2. So I draw a line segment with a slope of -2 and fill those in. At x is -2, the slope is -4. And I fill those line segments in. If you know an initial condition, such as 1, -2, you can sketch the curve. So I look for the point 1, -2, which is right there, and I follow the line segments in both directions to draw the curve. By following the slope field, you get a rough picture of what the curve looks like. In this case, it is a parabola. For more challenging differential equations, we will use a calculator to draw the slope field. For example, for dy dx equals -2xy over 1 plus x squared. On the TI-nspire, while in the graph screen, press Menu 3, Graph Entry Edit, 7 Differential Equations. We can enter the differential equation with the traditional vertical fraction, or the equation may be entered as y prime equals -2 times x times y1 divided by parentheses 1 plus x squared. Notice that we have to include the multiplication sign and replace y with y1. Leave the other fields blank and press Enter. If your calculator does not look like this, you might need to use Zoom Standard to adjust the viewing window. If it still doesn't look right, use Tab and the up arrow to get back to the Graph Entry Edit page. If the equation is correct, click here. We'll check the settings. The solution method should be Euler, although we're not using that today. Iterations between plot step is 1. The field is slope field, which is what we're trying to draw. The axes are default x and y. And we can scroll down and make sure the other entries match. Then highlight OK and press Enter. Integrals such as the integral from 1 to 4 of x squared dx are called definite integrals because we can find a definite value for the answer. The integral from 1 to 4 of x squared dx is 1/3 x cubed plus c, evaluated from 1 to 4, or 1/3 times 4 cubed plus c minus 1/3 times 1 cubed plus c, or 64/3 plus c minus 1/3 minus c, and the c's cancel out. In fact, the constant always cancels out when finding a definite integral, so we leave it out. We do not normally show the plus c in this step. So our answer is 63/3 or 21. Integrals such as the integral of x squared dx are called indefinite integrals because we cannot find a definite value for the answer. The integral of x squared dx is 1/3 x cubed plus c. When finding indefinite integrals, we always include the plus c. Many of the integral formulas are listed in your book. The first ones that we will be using are just the derivative formulas in reverse. Our book shows a technique to graph the integral of a function using the numerical integration function of the calculator, NINT, or NINT. Y equals the integral from 0 to x t sine t dt, or y1 equals NINT x sine x x0 x. This is extremely slow and is usually not worth the trouble. A better way is to use the calculator to find the indefinite integral and plot the resulting expression. That way the calculator doesn't have to redo the integral every single pixel across the screen. To find the indefinite integral on the TI-nspire, use the integral of x times sine x dx. We find the integral template with Shift+. Leave the lower and upper limits of integration blank, or you can push the delete key once to remove the boxes for the limits. Then enter the integrand and the variable of integration and press enter. Notice that the calculator leaves out the plus c. Now use Control-C and Control-V to put this expression in the graph equation and plot the graph. So we'll highlight sine x minus x cosine x and hit Control-C. Then go to the graph screen and hit Control-V to enter the equation. Press enter. And here's our graph.